Okay, our last speaker is François Pottier, and the talk is called Thunks and Debits in Separation Logic with Time Credits. Please take it away.
Thank you. Can you hear me okay? No? Yes? No. Okay, so this is joint work with Armaël, Guéneau and Jacques-Henri Jourdan, who are both here, and with Glen, Mével. So this is about thunks and more. But to begin, I'll introduce what thunks are quickly. They are a data structure which has only two operations. Creation takes a suspended computation and creates a new thunk, and force reads a result out of a thunk. And the idea is that the thunk data structure guarantees that the suspended computation is run only when necessary and run at most once. Using thunks, you can construct streams, for instance, which are also known as lazy lists in Haskell. And using thunks and streams, you can construct a variety of so-called purely functional data structures, many of which are presented in this famous book by Chris Okasaki from the end of the 90s. Now, Chris, in this book, uses thunks not only to enable a nice, purely functional programming style, but also to achieve good, worst-case amortized time complexity properties. And I should have said the banker's queue, which will appear later in the talk, is one of these data structures. So Okasaki achieves good complexity properties, and he also explains in English why this complexity, this good complexity, is achieved. And to do this reasoning, you might expect, when you hear the word amortized, that he uses credits, which are an idea introduced by Tarjan initially. And credit is something that you save little by little until you need it once in a while to pay for an expensive operation. That's the intuition of saving credits. But this intuition doesn't quite work here. It's actually unsound if you're naive about it, because credit is something that can be spent at most once, but thunks are data structures which are meant to be shared, and they're meant to be forced more than once without any coordination. So you cannot reason in a sound way about them using credits. So what Okasaki does instead is turn things around and reason in terms of debit. A debit is a debt. It's something that you have to pay before you're allowed to force a thunk. And duplicating debits is sound because it means you're duplicating a debt, so you're over-approximating the true time complexity of your program. And this kind of reasoning can be formalized, and it has been formalized as early as 15 years ago by Danielson in this POPL paper. This was done in a setting where thunks are primitive. And what we want to do here in this paper is go down to a lower level foundation. We want to view thunks as a library that can be implemented using mutable state. That's easy to do. A thunk is just a reference to either a suspended computation or its result. And to reason about imperative programs, of course, we are going to use Iris or some other separation logic, but in this case, Iris. And we're going to extend it with time credits. Time credits are not new. They go back to approximately 2010 in this paper by Atke, and also in several papers by myself and co-authors. And time credits are a very minimal extension to separation logic. All you have to do to extend your logic with time credits is to assert that there exists this assertion $n, which is an affine assertion which represents the ownership of n credits. And you're going to spend these credits to justify your computation step. So every step requires one credit and consumes it. So it's gone, and you can no longer consume it or use it afterwards. And of course, there is no way of creating new credits. So the credits that you are given initially are a bound on the amount of steps that you're going to be able to perform. So the idea in this talk is to build on this foundation to verify the data structures that Okasaki presented in his book. To begin with, we're going to have a ghost data structure because every talk in this session had a ghost data structure. So we have to do the same. I'll explain later what they're used for. They will come back at the end of the talk. And then using that, we will explain why it's safe to reason about thunks in terms of credits and debits. And then using thunks, we're going to move our way up towards streams, again, reasoning in terms of credits and debits. And at this point, we're going to see that we need something that is known as deep payment. which is a somewhat subtle rule which already appeared in Danielson's paper, for instance, but was not formally justified there. And one of the contributions in this paper is that we are the first, I think, to formally justify why this rule is sound. And finally, at the end, we verify several of Okasaki's data structures, and in particular the banker's queue, which I will briefly present in the talk. So at this level, we get relatively simple specifications for the queue where debits are no longer visible. We only see credits at this point, and the specification of extract, for instance, simply states that you need to give a constant number of time credits to extract. That's the capital X on the left-hand side of the precondition. And this means that the amortized time complexity of extract is big O of 1. So to summarize this introduction, we verify a few of Okasaki's data structures, and we explain debits and deep payment in terms of credits, and we do all this in the setting of separation logic with time credits. So to go a little more into the details, I will begin at the level of thunks and move my way up towards the upper layers, and then I'll go back to these ghost piggy banks at the end. So regarding thunks, briefly, they can be implemented in very few lines of code. This is an OCaml, a naive implementation of thunks in OCaml in 5 lines of code. So what we do in the paper is verify this implementation. And I'll just show the API that we get, the abstract reasoning principles that we establish about thunks. We have an abstract predicate, thunk, t and phi, where t is the address of the thunk in memory, n is the debit, so it's a natural integer, it's a debt, a number of credits that you will have to pay before you're allowed to force this thunk. And phi is the postcondition, it's an iris assertion which says what property will be true of the result once you force the thunk. There are 2 runtime operations, create and force, and several ghost operations, including sharing and paying. So I'll briefly move through these operations. When you create a thunk, the cost in credits is big O of 1, and if your suspended computation has a cost of n, then you get a new thunk which has a debit of n. So initially, you have done nothing, but you have something to pay. You can pay in several increments. So if your debit is 10, and you pay 2 now, then this consumes 2 credits, and your remaining debit is then 8. So in the rule, you see the debit decreases. And this is a ghost state update. It's an iris view shift. You can share thunks. Technically, this means the thunk predicate is persistent in iris. And this means if Alice knows the debit is 8, she can give this information to Bob and Charlie, say, and they can pay independently, which is very important. So if Bob pays 1, he knows the debit is 7, but independently Charlie can pay 8. He will know the debit is 0, while Bob still thinks the debit is 7. So several principals can have independent views of the debit. Here in this case, Charlie knows the debit is 0, so he can deduce the true debt is also 0, and this means he can force the thunk. Here we have this rule which says if you know the debit is 0, then you're allowed to force. And you get a value v which satisfies the postcondition of the thunk. So that's the basic thunk API, which already appeared in an earlier paper that we wrote in 2019. But the key missing rule is the deep payment rule, which I haven't shown yet. This is the ordinary payment rule, which consumes credits and reduces the debit. And the deep payment rule, somewhat counterintuitively, does the converse. It increases your debit and produces credits. So this might seem unsound, but the trick is that these credits are produced for use in the future when you force the thunk. The rule is a bit difficult to read, so I'll show a special case of it. The special case here has to do with 2 nested thunks. This is a thunk that promises to produce another thunk. And what the rule says essentially is that you can move the debit n2, the debit of the inner thunk, towards the outer thunk. So the total debt remains the same, but what you're doing is you promise to pay earlier. Or in other words, you're shifting your debits from the future towards the present, or to the left visually. So that's the rule that's difficult to justify, and which we justify using piggy banks. So I'll come back to it. Now, still moving up towards the upper layers of my picture. Streams are just sequences of nested thunks. That's the type definition. So we're going to get an API for streams, which is similar. We have a similar rule that allows sharing. We have a similar rule that allows shifting debits towards the left. What I should say is that we get this D vector, which is a vector of debits, because your stream is a sequence of thunks. You need to keep track in the logic of a sequence of debits. And shifting debits towards the left means you're allowed to redistribute the debits from a later thunk onto the preceding thunks. And using that, you can, for instance, replace an expensive thunk whose cost is n with many thunks whose cost is only 1. You can do this conceptual view shift without doing anything at runtime. And that's what is used in the analysis of the banker's queue, actually. The banker's queue is a FIFO queue where every operation has constant amortized time complexity. Once in a while, this expensive list reversal operation is required here in the middle. And in terms of the complexity analysis, what happens is that this append of Revel expression constructs a stream where one thunk in the middle is very expensive. But that's okay because its debits can be shifted towards the left. So conceptually, we end up with many thunks whose debit is only O of 1, and that's why we can justify that extract has constant time complexity. Now, in the remaining time, I would like to say a few words about ghost piggy banks. And so these are almost like thunks, except they involve no code at all. So the idea is to try to extract the essence of debit-based reasoning without verifying any actual code. So we will have the same operations as for a thunks, essentially, creating, forcing, paying, sharing. No deep payment here, just simple payment. I don't really have time to go through the rules, but sharing and paying are the same, essentially. When you create a new piggy bank, you set a target amount, so you're declaring how much credit you hope to collect, and you also set a target property, so you say what property you hope to establish once you get that credit. I'll skip the forcing rule, but the point of all this is that these piggy banks are easy to verify, to explain, because they don't support deep payment, but they are a useful building block in justifying deep payment. And when we construct thunks, what we do is initially, every time a new thunk is created, we create one piggy bank for it. So we have one piggy bank per thunk, and that's a simple idea. But what is less obvious is that when someone makes a deep payment on an existing thunk, we conceptually create a new piggy bank for it because we want to be able to set a new target amount and a new target property, and that is something that we don't know how to do without creating a new piggy bank. And this idea is something that was implicitly present in Okasaki's book, where he says you need to reason about the debits for a thunk that does not even exist yet, and when you're doing that, you're essentially manipulating ghost state. So it's not really surprising retrospectively that this kind of ghost data structure is needed. That's about it. So in summary, in this paper we explain debits and deep payment in terms of credits, and the novelty is really deep payment, which wasn't explained in earlier papers. In the paper we also have details about forbidding reentrancy and guaranteeing that our streams are productive. And we verify not just the banker's queue, but also two more data structures. We haven't done all of the data structures in the book, so there is more work for you to do. And regarding future work, one open problem that I would like to mention is also if you are looking at something like concurrent code where you have a loop that waits until some good event happens, then this loop has unbounded waiting time, and we don't really know how to reason about it using credits. Thank you.
Questions? Robert first, and then.
Thank you for the talk. I have two questions. One, you showed a lightning strike symbol thingy somewhere. Yes. What is that? So this slide is relevant. So the lightning symbol here is an affine token. It's a unique token that is carried around, and it's used to prevent you from having two threads which concurrently try to force the same piggy bank or force the same thunk. Essentially, our thunks are a non-thread safe data structure, so we need to have some kind of restriction which prevents you from
from racing to force a thunk.
Maybe the logic of the second speaker in this session would be an alternative.
I don't know.
Okay, that was not. Let's leave that open. My second question is: you said that improving the. Can you go to the conclusion slide? Making Iris dollar more user-friendly would require some engineering work. What is not user-friendly, and what would be required?
Yeah, at the moment, so Iris dollar is Iris with time credits, and the way we implemented it is via a kind of translation into normal Iris. And this translation is not as opaque and abstract as it should be, so sometimes you have to unfold it, but sometimes it unfolds automatically without you wanting to unfold it.
So the translation at the level of the programming language or at the logic?
It's a translation of the program. Basically, the translation adds tick instructions everywhere in the code. And reasoning in Iris dollar about the program is the same thing as reasoning in normal Iris about the program instrumented with ticks.
Oh, so you're always verifying a program where the translation is applied. You always have a word triple of translate of program.
Right.
Okay. Yeah, I see.
There are questions over there. No. Can you raise your hand, whoever was to, please? Yes, go ahead.
Okay, so I'll give you the mic later, I guess. Yeah, I was wondering, because you said that you can move your depth credit, your debit from a later thunk to an earlier one, and I didn't quite get how do you determine that a thunk is earlier than another thunk?
It just has to do with the nesting of the thunk predicates. As in this example, you have a thunk at the outside, and then in the post condition of this outside thunk, you have another thunk. So the one on the right is nested in the post condition of the outer thunk.
Okay.
And in that case, you can shift the debits towards the outside or towards the left visually.
Okay. Okay.
Over there.
When you were on one of your first slides and talked about debits and credits, I was immediately thinking about debits as linear resources, but this is not what you are doing.
No, indeed.
Could you comment on whether, if you did something like that, could you design different proof rules, or can you give some intuition about why that wouldn't be a good idea?
Well, the debits are inherently associated with a thunk. So, yeah, maybe we could make them a linear predicate, assuming we have a separation logic which supports linear assertions, which Iris doesn't at the moment. But assuming we have that, maybe we could view the debit as a linear resource. But I don't see how that would be easier to use or better than what we have at the moment.
The one point is that it is persistent, right?
Yeah, the thunk predicate is persistent. This is a key feature.
Okay, thank you.
Any other questions? Okay.
Thank you. I was just wondering how does this compare to works that are more type theoretic approaches to proving automatically these types of complexity results? So I think it's called automatic amortized resource analysis. Do you view this as kind of being more powerful but needing more human intervention?
I think this system here with time credits, which is at the bottom of the slide, is extremely expressive. And it's also not automated at all, but you can do a lot of things. And in particular, if you take the ARA systems that you mentioned, they have automated inference. And I think they're less expressive, and they can be translated into this. The safety of an ARA type system, I think, can typically be proven by encoding it into Iris with time credits.
One last question by Amin, and then we're done.
Yes, you said that your thunks are not thread safe. But then you said that one of the open problems is unbounded weighting. Is that in a concurrent setting then, or?
Yeah.
or what?
So at the moment, our thunks are not thread safe, but the logic we use allows threads. So you can use thunks in a multi-threaded programs as long as you take necessary precautions to synchronize your accesses to thunks. And this open problem is not really related to thunks at all. It's just a general problem about Iris with time credits and how to reason about concurrent code, but not connected to thunks.
I see. Thank you.
Okay, let's thank François once again.